Section 14.3, Partial Derivatives. We defined the derivative in single variable calculus in a way that would give us the slope of the line tangent to a curve. But in multivariable calculus, we have surfaces and not curves. So if we look at a surface, we have an infinite number of tangent lines we could potentially draw at any point. You just pick a direction, you could draw a tangent line anywhere. So which one do we pick for our derivative? Should we even pick one for our derivative? If there's an infinite number, you could just say, okay, well, maybe the derivative should just be undefined for surfaces. But then, we just, stop at calculus at 3 dimensions? No. So what we can do is, how about we pick 2 different ones? We'll pick one that's parallel to the y-axis, and we'll pick one that's parallel to the x-axis, and we'll say that those 2 different derivatives are the partial derivatives of the function. One with respect to x we'll call fx, and one with respect to y. And we'll do this by making the other variable constant. So if we take a partial derivative with respect to x, we'll pretend that y is constant. That way we get a slice of the surface, which results in a curve. And then we just take the tangent line, we look at the tangent line to that curve, and we look at the slope of the tangent line to that curve. So we could also slice parallel to the x-axis, in which case our surface becomes a curve parallel to the x-axis. We take the tangent line there, and we look at the slope, and then that's that derivative. We could still take derivatives in infinite other directions as well, but we'll just look at these 2 to start. So in general, if f is a function of 2 variables, x and y, and we let x vary while keeping y fixed, so we set y equal to constant b, then we suddenly have a single variable x. We have a function of a single variable because y is suddenly constant. So we could take the derivative the same way that we did in single variable calculus, as the limit of this single variable function g, where y is constant, plus h minus g of a over h as h tends to 0. So that's the same thing as just putting in f of a plus h comma b for that constant that we put for y. So we can also do this with respect to y by holding x as a fixed constant, say x equals a for some point a, b, and then looking at that limit. And then that'll be the partial derivative with respect to y. So if we let this point vary, this point ab, then we get the partial derivatives as functions in general. So we have fx of xy as the limit of fx plus h comma y minus fxy over h, where we hold y as a fixed constant at each individual point, but we let the point vary over all different points. So that means that we slice the curve at all different points where y is a fixed constant. Then we look at the tangent lines to all those curves, and we look at the slopes of those tangent lines to those curves we get from the slices. We do the same thing for x being held constant. We get parallel to the y-axis, and we make all of those slices, and then we look at those tangent lines, and we look at the slopes. We have some notation for partial derivatives. Nobody can really decide what the best thing is, and actually it depends on context. So we'll often use f with a little x underneath to denote the partial derivative with respect to x. That means y is held constant. But sometimes we'll say partial f partial x using this little del operator over here for partial derivatives. And sometimes I'll just write that as, or read that as df dx because I'm lazy. We can also say that's the operator applied to f. We can also just throw in z for f if z is a function of x and y. Sometimes people write f1 to denote the first variable, in this case x, but I think that this is actually confusing notation, so we'll probably stay away from that. So to find the partial derivative with respect to x in general, what we'll do is we'll probably not use this limit very often. Instead, we'll just pretend y is a constant, and we'll just differentiate with respect to x, assuming that y is just some constant. We'll just pretend it's like 2 or something. And then we'll do the same thing to find the partial derivative with respect to y. We'll regard x as a constant and differentiate as normal. So let's do an example. How about we have this multivariate function. Let's find the partial derivatives with respect to x, with respect to y at the point 2, 1. So let's look at the partial derivative with respect to x in general. Well, we'd treat y as a constant, so our first term, x cubed, is just differentiated as normal with the power rule, 3x squared. Then over here, we've got x squared times y cubed, and it looks like a product, but it's not, because the y cubed is a constant right now. So pretend it's like x squared times 2. So then you would just differentiate the x squared and keep the 2. So that'll be 2x times 2. So in this case, it's 2x times y cubed. And then this is a constant, so the derivative is 0. So now let's plug in a point 2, 1. So we get 3 times 2 squared plus 2 times 2 times 1 cubed, which is 16. Okay, how about the partial derivative with respect to y? So now we'll pretend that x is constant. So that means that this derivative is 0, it's constant. If we look at this guy, this is some constant times y cubed. So we take the derivative of y cubed, which is 3y squared, and we keep our constant. So we get 3x squared times y squared. And then that's just a function of y, so minus 4y. So our partial derivative at 2, 1 with respect to y is 3 times 2 squared times 1 squared minus 4 times 1, which is 8. Let's do another example and find some more partial derivatives and interpret their numbers as slopes. So we have the partial derivative with respect to x. Well, 4 is a constant, so it's gone. And 2y squared is constant, so it's gone. So we just have minus 2x. So plugging in for 1, 1, we get minus 2. How about partial with respect to y? Well, then constant, so it's just minus 4y by the power rule. So our partial at 1, 1 is minus 4. In order to interpret these numbers as slopes, how about we try drawing this thing over here for minus x squared minus 2y squared. So it looks roughly something like this. Let's see if I can do it. Okay, we'll put in the z-axis over here. And we'll put in y-axis. And x intersects at 2. For the x-intercept, you can just plug in 0 for y, so you get x squared would have to be 4. And what I want to do is I want to take this curve, or this surface, c equals 4 minus x squared minus y squared, or minus 2y squared. And I want to slice it so that we're parallel to the x-axis at 1, 1. So I need a slice. How about I use green? Let's see if I can do this. Okay, so something like that. So this slice is at constant y equals 1. So notice that it intersects the my surface in a curve. Remember, there's nothing inside the surface, it's hollow, it's just the surface part. That's what we call a surface. So this curve is something that I can take a tangent line to. Oh, by the way, here's the point 1, 1. And over here, floating above it, is the point 1, 1, 1. So how about we look at the tangent line now? So here would be the tangent line to that curve. How about we call it C1? So I'm naming the curve now. Should probably be a little bit more clear where the arrow is pointing to, though. This arrow is pointing to this entire slice, whereas I'm just pointing to the curve itself. So that's going to be the curve C1. So I get this tangent line, and let's say that the slope of the tangent line to the curve C1 we get by slicing at 1, 1, 1 is the partial derivative at 1, 1 with respect to x, which we calculated was -2. Which makes sense if you look at this in the xy plane, or you try looking at, let's say, this curve in the xy plane, then you could draw the curve as going sort of downwards like that, so it makes sense the slope of the tangent line would be negative. How about we do this exact same thing again for the partial derivative with respect to y? So again, I'll try to draw the exact same surface. Good luck with that. It's already looking a little bit different. And I'll throw in my z-axis again. My y-axis. And x. And I need to take a slice now, but I want it to be parallel to the y-axis. So let me switch. Let's try doing it something like this. That didn't come out very good. I want the slice to be kind of, hang on. Let's see, something like that. Yeah, it's a little better. Okay, so I've got my slice now, and it's at constant value x equals 1. So here's the point 1, 1. It's in the same place as it was before in the xy plane, and here's the point 1, 1, 1 in the same place it was in the xyz plane, not plane, three-dimensional space. What we want now is to look at the curve that we get from the slice, which is C2, because I'm just going to name it C2, why not? And we need to see what the slope of the tangent line is over there. So here's the tangent line. So it looks like, again, it should be negative, which it is. We calculated it was -4. So we could say the slope of the tangent line to C2 at 1, 1, 1 is the partial derivative with respect to y at 1, 1, which is -4. Say the body mass index of a person is defined by B of mh equals m over h squared. Let's calculate the partial derivatives of B for a young man with mass 64 kilograms and height 1.68 meters and interpret them. So we'll do partial of B with respect to m, and I'll leave it in the mh notation. So that's going to be the partial with respect to m of m over h squared. So that's, well, notice that h squared is a constant. So this is like saying x over 2, for example. Your derivative would just be 1/2, because we just have this one variable. So this is just the constant 1 over h squared. If I want the partial derivative with respect to m at 64, 1.68, and I just plug that in this case just the 1.68, and I get 1 over 1.68 squared, which is about 0.35. So we started with mass over height squared. So we started with kilograms per square meter, and then we took another, we took a partial derivative with respect to mass again, so that means we get another per kilograms. So it's kilograms per meter squared per kilogram. This is the rate at which this body mass index changes with respect to weight, so we could write that. Rate at which the BMI increases with respect to weight, and it's at this 0.64, 1.68, so that's when this person weighs 64 kilograms and is 1.68 meters tall. And when we say with respect to weight, we mean that the height is constant. So that means that if this person stays 1.68 meters tall and then goes up in weight by a certain amount, then we would expect that the body mass index will change by this amount. And if it goes down, then it would decrease by this amount, assuming that the height is constant. And we do pretty much the same thing to get the partial with respect to height, so let's do that now. So dB dH, I'll call it, is the partial with respect to h of m over h squared. And notice now we just have 1 over h squared. M is constant. This is like 2 over x squared, for example. So then the derivative of 1 over x squared is just minus 2 over x cubed, because you write it using the power rule. And if you want, you could even just pull out this constant. So we get m times minus 2 over h cubed, which is minus 2m over h cubed. So the partial of b with respect to h at 64, 1.68 is equal to minus 2 times 64 over 1.68 cubed, which is about negative 27 kilograms per square meter for our BMI. And then this is with respect to height, so it's per meters. A little bit confusing the way that I used m for meters and m for mass, because this m means meters for the height and this m means kilograms for the mass, but they're different m's, but that's okay. So this is the rate at which BMI increases with respect to height at 64 kilograms and 1.68 meters tall. So that means that if this person kept their weight constant and just grew a couple inches or somehow lost a couple inches, then well, let's say they grow a couple inches, and their body mass index decreases, which makes sense because thinking about if they're taller but they weigh the same amount, their BMI should go down. But if they were to somehow lose height, then their BMI would go up because their weight hasn't changed. Okay, how about we try to get these partials when we have a sine of a function. So we have a function composition. Looks like we need our chain rule from single variable calculus. So we'll try to get the partial with respect to x first. If we're pretending that y is constant, this is like sine of x over some constant. So using the chain rule, that's cosine of x over our constant 1 plus y times the partial of what was inside, which is x over 1 plus y. So that's just the cosine of x over 1 plus y times 1 over 1 plus I. Its derivative of x is 1, and 1 over 1 plus y is a constant. Okay, how about with respect to y now? So that'd be the cosine of x over 1 plus y again. But this time we're taking the partial with respect to y of the inside. So we'll regard x as a constant. So taking 1 over 1 plus y as the derivative, it's like 1 plus y to the minus 1. So we'll take the minus out. We have cosine of x over 1 plus y, and we have 1 over 1 plus y squared with the minus over here. So we keep our x, our constant, and we put 1 plus y squared in there. Okay, let's find the partials with respect to x and y if z is defined implicitly. So we'll use some implicit differentiation like the way that we used to. How about we first differentiate implicitly with respect to x? So given our equation over here, we have 3x squared by the power rule. And then with respect to x, so the y cubed disappears. And then we've got z cubed. Z is a function of x and y. So this is like when we did implicit differentiation where we had to be careful of all of the y's in there because they were functions of x. So we need to make sure that we multiply by the partial derivative when we take that of z cubed because we don't know what it is. So we'll differentiate pretending that it's like our x, so we get 3z squared, but we'll multiply by partial z with respect to x using our chain rule from single variable calculus. So the partial differentiation is pretty much the same thing as it was before. Now look at 6xyz. X is a variable, y is a constant, so we can forget about it, but z is a function of x. So this is a product of 6x, you could say 6xy and z. So how about I take the derivative of 6xy first? So then, if I do that, 6 times y is the constant, so that's all I have left. And then by the product rule, I still need my z without the derivative. Then I need to differentiate the other part, so I keep the 6xy, don't differentiate that, and now I'll need to differentiate z. So that's partial z with respect to x. And then differentiating 1 just gives 0. So we move everything over, we move these guys to the Actually, it's probably easier to move everything else to the other side. And then we factor this guy out and divide. So we get partial z with respect to x is equal to minus x squared plus 2yz over z squared plus 2xy. And we can do the same thing for y. So if we take this equation and we partial differentiate with respect to y, then we get 3y squared, because this is constant, and we get, again, 3z squared, but this time the partial is with respect to y. And then if I'm looking at this, now I've got my product a little bit different. 6x is a constant, so this is 6xy. It's still this product rule, but we have to think about this a little bit differently. When we take the derivative of 6xy, and y is the variable, then we just have our constant left, so that's 6x. And then the other part of our product is z. So we apply that without the derivative. Then we've got 6xy without the derivative, and then z with the derivative. And that's going to be 0 also. And again, we solve for our partial derivative that we want, and we get that it's minus y squared plus 2xz over z squared plus 2xy. Maybe you can see by now, but throwing in another variable should just make this process pretty much the same. We just keep looking at it as a single variable function where every variable that we don't want to have to deal with is just regarded as a constant. So if we've got 3 variables, for example, we want the partial with respect to x, then we treat y and z as constants, and we just look at the function of x. And in general, if we have some function of n variables, then the partial derivative with respect to the ith variable, xi, which could be any of these variables, is just the function with that xi plus h, and then all the other variables are treated as constants. We also sometimes write du dxi, or partial of f with respect to xi, or whatever it is. This process is pretty much the same as before. For example, let's look at this function over here, e to the xy, ln z. In this case, we don't have to use implicit differentiation because we're thinking of it as a function of 3 variables. So if I want the partial derivative with respect to x, then I treat both y and z as constants. So this is e to the x, let's say, times e to the 2x, for example, times, 4, because this is just a constant. So e to the 2x would just be 2e to the 2x, so e to the xy is just ye to the xy, and then we just keep our ln z because it's constant. If I want the partial with respect to y, it's pretty much the same thing. It's e to the y, and then there's this x constant in the way, so I pull that out. So that's x e to the xy times ln z. And then if I want the partial derivative with respect to z, well, notice that this is just some constant times ln. Derivative for ln is 1 over z. So this is just e to the xy, my constant, over z. If f is a function of 2 variables, then its partial derivatives are also functions of 2 variables. So we can take their partial derivatives the same way that we took second and third derivatives before. However, we have more options this time. We can either take the partial derivative with respect to x first and then x again, or we can switch it up, and after taking the partial derivative with respect to x, we could take it with respect to y. Similarly, we could take with respect to y and then x, or with respect to y and then y. So we have 4 different options now. We'll write these partial derivatives as either fxx, fxy, fyx, fyi, or we'll apply the partial notation to our partial, or we'll write it as, just like we did d squared y over dx squared, we'll do partial squared f over partial x squared over the z, depending on what we want to use. Okay, so you have to be kind of careful here because this notation means that we first differentiate with respect to x, and then we do y. But when you look at, let's say, this notation over here, notice the order is different. Because this comes from, like function composition. This is like f of g, in which case you do g first and then f, whereas this is written in the order that you would normally read in. So you got to be a little bit careful. The notation can be confusing. How about we find the second partial derivatives of this function over here? So let's find the first partial derivatives. We have fx is equal to, let's see, 3x squared for that guy, plus 2x, because that's the function, and then y cubed is constant, so I'll just keep it. And then that's constant, so it's 0. If I want the partial with respect to y, then that's just, this is constant 0, and then we've got 3y squared times the x squared, so I'll write that as 3x squared y squared, and then minus 4y. Okay, let's take the second partial with respect to x, for example. So that'll be the partial with respect to x of 3x squared plus 2xy cubed, which, well, that's just 6x. And over here, this is our variable, so we just have 2y cubed. Okay, how about I want the partial with respect to x, and then how about I do y after? So that'll be the partial with respect to y of this 3x squared plus 2xy cubed. So I'll do 3x squared plus 2xy cubed, and I'm taking the partial with respect to y, and I get, well, that's 0, so I just get 3y squared, so 6xy squared. Okay, how about if I want partial with respect to y and then x? So that would be the partial with respect to x of this guy. So that's 3x squared y squared minus 4y. So that's constant 0, so I just have 6x y squared. And last but not least, partial with respect to y and then y, so that's just the partial with respect to y of 3x squared y squared minus 4y, which is 6x squared y minus 4. Notice something kind of cool here. The partial with respect to x and then x was totally different than partial with respect to y and then y, which is what we would have expected. But the partial with respect to x then y was the same as the partial with respect to y and then x. They're both 6xy squared. So this leads us to our next theorem. Turns out that if f, assuming certain hypotheses, the mixed partials fxy and fyx are equal to each other, you need f to be defined on a disk that contains our point, and then you need the functions to be continuous there. And if those partial derivatives are continuous, then they will be equal to each other over there. So that's kind of cool. We only have to compute one of them, that means, and we get the other one, assuming continuity and assuming a function is nice enough. Okay, so partial derivatives of order 3 or higher can also be defined. For instance, we could get the partial with respect to x, then y, and then y. And it can also be shown using Clairaut's theorem that these mixed partials, if you do x, then y, that's the same as doing y, then x, then y, and it's the same as doing y, then x, assuming that all of our functions are continuous. How about we get like a fourth partial derivative of this function over here? So it's a function of 3 variables. So we'll start with partial with respect to x, because that's our first one. So that's going to be, let's say, sine of this thing, so that's cosine. And then the derivative of the inside, notice that we're treating y and z as constants because we have 3 variables. So we just have 3x. So we just have 3 times the cosine of 3x plus yz. Okay, what if we want to take another partial with respect to x of that? So we get, well, again, this is constant, so we'll just pull out the 3. And we'll take the derivative of cosine, which is minus sine, so we get minus 9 times the sine of 3x plus yz. Okay, how about we go now with respect to y? So with respect to y, this is constant and this is constant. So z is the constant I pull out. So I get minus 9z times the cosine of 3x plus yz. And now, last but not least, we will take our partial derivative with respect to z. Okay, well, over here, we have a little bit of trouble now because this is a function of z, and this is a function of z, so we have to use the product rule. So I'll do this derivative first, so that's just minus 9. And then I'll just leave this cosine of 3x plus yz without the derivative. And now I'll leave my minus 9z, and then I'll take the derivative of this with respect to z. So that means the y hops out as it did before, and we get minus sine, so the minus cancels, and we just get plus. So I'll have plus 9yz times the sine of 3x plus yz. The partial differential equation d squared u over dx squared plus d squared u over dy squared. So basically we're taking a partial with respect to x twice, we're taking a partial with respect to y twice, and we add those partials together and we get 0. That's called Laplace's equation. Solutions to this equation are called harmonic functions. So how about we show that the function e to the x sine y is a solution of Laplace's equation. So we just need to take the partials twice that aren't mixed and add them together. So let's get ux first. So if we treat x as the variable, then this is constant, and derivative of constant times e to the x is the same exact thing as we started, so this is just e to the x sine y. And then we'll take the partial with respect to y. So taking this is just constant, so derivative of sine y is just cosine y. So we have e to the x times cosine y. Okay, let's take the second derivative now. So with respect to x, again, you can take it as many times as you want. You'll still have e to the x sine y. And then we'll take this guy again with respect to y, and we get minus e to the x sine y, because we only have to worry about this because this is constant. Okay, let's add these guys together. So we get uxx plus uyy. Well, that's just going to be e to the x sine y minus e to the x sine y, which is 0. So it is a solution of Laplace's equation. Last but not least, the wave equation, where the second partial with respect to some variable t, we'll use t instead of y here, is equal to some constant squared times the second partial with respect to x squared. So that describes the motion of a waveform. It could be an ocean wave, sound wave, light wave, or wave traveling along a vibration string. Let's verify that this function over here satisfies the wave equation. So I'll take the partial with respect to x. I get ux equals the cosine of x minus at, because in this case t is constant, so we just have sine of x basically. And then and I'll take the partial with respect to t. So in this case, t is my variable. It has a coefficient of minus a, so that hops out in front. And I get cosine of x minus at again. Okay, how about we take the second partials? So I get, this was minus sine times x minus at. So it's just derivative of cosine, and then I get the second partial over here is equal to, well, this a hops out again, minus a, so I get minus a squared times the sine of x minus at, because this minus hops out and cancels, but then derivative of cosine is minus sine. Okay, so this is utt, that's this thing over here, which is equal to a squared times minus sine x minus at, which is uxx. So this equation is satisfied, just using a little bit different notation. So we verified that this function does satisfy the wave equation.